Okay, so we're at the conclusion. We're at the conclusion of studying our theoretical study of bonds and reactivity. Then we'll go on to something completely different. And we're ending by talking about reactivity in terms of 4 functional groups. And you're doing your own functional groups, remember, for tomorrow. Okay. So we already talked about carbonyl last time. And now we're going to go on to amide, carboxylic acid, and alkyl lithium as other functional groups. And then we'll do something just completely different for the next quarter of the semester. Okay, so resonance is homo-lumo mixing that happens within a molecule. The molecule, of course, knows all about it. It only becomes resonance because we draw a picture that's too simple and we need to modify the picture, right? And that modification is called resonance. And a good example of that is the amide functional group. Now, when I include an amide on the first exam where people are supposed to identify functional groups, circle them and name them, it's inevitable that some people will circle the C double bond O and say that's a carbonyl group, and some people will circle the nitrogen and say that's an amine. But an amide is not an amine, and it's not a ketone or a carbonyl group. It's its own thing. And the reason is that those interact with one another in a way that makes them no longer like an amine and no longer like a carbonyl group. That's resonance. So we'll look at it here in terms of 2 different pictures of the molecule. One is as a carbonyl amine, and the other is as an amide, which if you're into Lewis structures, you draw with a double-headed arrow and show two resonant structures. And in the carbonyl and amine, you identify a homo that makes the thing a base and a lumo that should make it an acid. But resonance can be thought of as a reaction already within the molecule between the homo and the lumo. And it's a make and break situation, just like we saw between molecules last time, where the unshared pair makes a new bond, in this case the second of a double bond, and something leaves from the carbon that's being attacked. The thing that leaves is the second bond of a double bond. So it's another one of these make and break situations, but in this case, it's a correction to our naive, localized picture that we drew at the beginning. Okay, so let's see about this. First, we have the naive prediction, what that should say about the characteristics of the molecule, and then what the experimental observation is, which requires that we use something more complicated, the resonance structures, or thinking in terms of molecular orbitals. Okay, so the amines and carbonyls are perfectly stable molecules in terms of being low energy. They don't just do something. But what's associated with the idea of resonance structures is the thing is more stable than you would have predicted if you didn't consider the resonance structure. So you say that's more stable, and you can see why it would be more stable, because the unshared pair is mixing with a vacant orbital and becoming lower in energy. Okay. In fact, the observation is that it's more stable by about 16 kilocalories per mole, which about 1/4 as much as a carbon-nitrogen bond is worth. So it's a significant amount of energy. Now, if you have a CN single bond, that's longer than a double bond, and longer than a partial CN double bond that you'd have for the average of the resonance structures on the right. And in fact, that bond is shorter than normal single nitrogen carbon bonds by about 0.14 angstroms. Okay? On the left, you have a short double bond for C double bond O. But on the right, it's a partial single bond, so it should be longer, not held as tightly. And in fact, it is longer than other CO double bonds by about 0.03 angstroms. Okay? We've seen before, when we were talking about XH3, why nitrogen tends to be pyramidal, so as to give S character to the unshared pair of electrons. But on the right, if it's going to be part of a double bond, it has to be planar. And we can see why that is. So here's the pi star LUMO of the C double bond O. And here in front is the unshared pair on nitrogen in a p orbital, which overlaps and delocalizes, mixes with the vacant LUMO, right? That means that you have a partial double bond for the CN and a partial single bond for the CO. How is it that putting in electrons makes it a single bond rather than a double bond? Why would putting in electrons weaken a bond? Alex? Can't hear. Because it's an antibonding orbital, the pi star of CO. Okay? Now, so it's planar indeed, and I'll show you pictures that prove it, because it gives the best overlap. If there were an sp hybrid on the nitrogen, the s part of it wouldn't overlap with the p pi. So a pure p orbital gives the best overlap. So that's why it's planar from a molecular orbital point of view. Now, if you have a single bond, it's easy for things to rotate around it because it's cylindrically symmetric. But we know that a pi bond is not cylindrically symmetric. It has that oval shape. So there's a barrier to rotation about the central bond of a carbon double bond. Because when you rotate the nitrogen in front like this by 90 degrees, you've wrecked the overlap that allowed those electrons to be stabilized, right? In fact, once you've done this, there's no reason for the nitrogen to be sp squared hybridized anymore because the unshared pair is not trying to overlap with the carbon p orbital behind it, right? So it might as well hybridize and become sp squared the way it normally does. And this structure, the halfway rotated structure, turns out to be 16 kilocalories more stable than the one, or pardon me, less stable than the one where you do have the overlap. So twisting it has a barrier of 16 kilocalories per mole. Have you ever seen that number before? Zach? That's what we saw at the beginning. It's more stable when those electrons can be stabilized as compared to an amine and a carbonyl that are not interacting. Because when you turn it 90 degrees, they indeed are not interacting because they're orthogonal. Okay. An amine, as we said, should be basic, and a carbonyl should be acidic because of the low LUMO, the pi star CO. But if they mix with one another, then the HOMO is lower and the LUMO is higher. So they're not reactive anymore. They're not as unusual in their highness and their lowness, right? So it turns out that amide is relatively unreactive. Now, do you know, relative to what you'd expect for an amine and a carbonyl. Now, do you know where you encounter amides all the time? You can touch an amide with no problem. How? Sophie? Pardon me?
They're amino acids.
Amino acids, which make proteins. Amino acids aren't amides, but proteins, which are made of amino acids, an amine reacting with a carbonyl, those are amides. And you want them to be stable. Why? You don't want them to be reactive like a carbonyl and an amine. It's so your skin works. Otherwise, in lab, if you, what does a base, if you feel sodium hydroxide, you've done this, what does it feel like? It's slippery. If amides weren't unusually stable, right, then when you felt it, your skin would go away, right? So it's a good thing. In fact, and the last thing is also important. So you're opposing dipoles mostly, right? Carbon to oxygen is plus towards carbon, minus toward oxygen. Carbon nitrogen, plus toward carbon, minus toward nitrogen. But mostly those two are opposed to one another. And a little bit they add. So you get a net displacement of positive negative charge in the molecule from left to right, positive to negative. Okay? That's what would happen if it were a carbonyl and amine. But it's not a carbonyl and amine. It's strongly dipolar, not canceled, and it's in this direction, perpendicular to the original direction, because you take electrons that were on nitrogen in the amine and you shift them into the carbonyl group. So it's as if the magnitude of that effect is as if you transferred 1/3 of an electron from nitrogen to oxygen. If you did that, you'd get as much displacement of charge on average as there actually is, right? Now, it turns out that all these latter properties are crucial for structural biology. We already saw that if you want skin to work, it has to not be as reactive. But these other things are important too. The geometric things, that nitrogen has to be planar and that there's a barrier to rotation, is very important. And also the dipolarity, the direction of the dipole, is very important, and we'll show that. So here's an amide bond. Okay, the nitrogen is blue and the oxygen is red. You see the double bond. But you shift electrons from the nitrogen to the carbonyl group, and that is the pi star. That's the HOMO, not the pi star. It's the HOMO. The pi electron pair, which is shifted from nitrogen and shared with the C double bond O. Now, that sharing, as we just said on the previous slide, creates an electric dipole. So the electrons are shifted in the direction shown. And that's crucial, because here is a picture of a helix, an alpha helix of a protein, and I outline the backbone of it there. Okay? So several turns of an alpha helix, which has a lot of amide bonds in it. And if we look at it, we see there's an amide, there's another amide, there's another amide, all on, more or less on the top of this helix. What's interesting about those? Andrew, what's interesting about the set of them? How are they lined up? Do you think it's favorable or unfavorable, the way they're lined up? Plus, minus, plus, minus, plus, minus in a row. They're all lined up so as to be attractive to one another. So that stabilizes this structure. In fact, another way of talking about it is to say, as shown here by these deltas, that the oxygen is partially minus and that the hydrogen attached to the nitrogen is partially plus. So getting this minus near that plus is favorable. What do you call that? Anybody know? That is a hydrogen bond, right? So you have, it's stabilized by electrostatic interaction, these hydrogen bonds. Not only there, but there are other ones too, like here, a chain of them there, and another chain down here at the bottom. So this helix is stabilized by the fact that the dipole points the way it did. If it pointed in the perpendicular direction, you wouldn't get this stability. Okay? And it's also stabilized by the geometry that's favored, the local planarity, the fact that you don't twist around the CN double bond. So here's the partial double bond. So here's carbonyl, here's the CN, and that's partial, although it's written as a single bond, it's partially a double bond. So you don't twist about it. So this atom, this atom, this atom, this atom are all in the same plane. Right? And you see another such group here, back behind, where here is the bond in question. So this atom, this atom, this atom, this atom are all in the same plane. Or here at the bottom, you see it, where you're looking almost in the line, in the plane, right? And what does that mean? It means that the backbone is not as floppy, because you take away some of the possibilities of twisting it. So it helps it take this shape. So both the dipole and the geometrical freezing of some of the single bonds means that this structure is particularly stable and therefore very prevalent in biological macromolecules. So that makes a lot of difference that amides are amides and not amine carbonyls. Okay, now how about carboxylic acids? That's the next functional group. So let's compared with what are they acidic? Compared to alcohols, because you might think that in the same way that an amide is an amine ketone, you might think that a carboxylic acid is an alcohol ketone, but it's not, right? They interact with one another in much the same way. Now, if you had just a regular old alcohol, it can dissociate as an acid. It's not very strong as an acid. You don't burn your skin with it, right? But it has a pKa of 16. That's the dissociation constant is 10 to the minus 16. That's not very impressive. But for a carboxylic acid, the reason it's called an acid is because its pKa is much lower. It's more acidic. The equilibrium constant's 10 to the minus 5, so it's acidic. It's not an alcohol. It's 10 to the 11th times stronger than an alcohol, right? And why? Now, why? Well, just like an amide, you have an unshared pair on the OH oxygen, which could be stabilized by the pi star orbital of the C double bond O. Now, if that stabilizes the material on the left, how should it affect the equilibrium constant? Should it be at more or less acidic? That is, because of this interaction, because of this resonance structure, we could say, because this pair of electrons is stabilized by the carbonyl, there's a factor that's stabilizing this which doesn't exist in the alcohol. So you're stabilizing the material on the left of the equilibrium. Would that tend to make it more acidic or tend to make it less acidic if it's stable on the left? Right? So you have, here's the stuff on the left, here's the stuff on the right. It's uphill in energy. No matter what you're talking about, it's hard to dissociate as an acid, right? So I make this more stable, which is what I just showed. There's resonance here that stabilizes this, homo-lumo mixing within the molecule. Does that make it more or less easy to dissociate? Harder or easier? Harder, right? It's further uphill. So this seems backwards. The stabilization that we saw in the analog of the stabilization we saw in an amide that makes your skin not dissolve has the opposite direction. It predicts that the dissociation would be more uphill, where in fact it's less. Why? Because if we look at the product, you also have homo-lumo interaction between an unshared pair on this oxygen and the carbonyl. And that will stabilize it on the right and make it easier to dissociate. Which should be more important? The amount of extra stabilization on the left, here's what it was for an alcohol originally, right? We stabilize it on the left and we stabilize it on the right. Which is more stabilized? The carboxylate or the original alcohol? The carboxylic acid. What do you know from the fact that it's more acidic, which must have gone down further? This one must have gone down further. Can you see why? Why would this one be more stabilized by homo-lumo mixing, that is, this be more important, than it is here with that? Lucas?
Symmetry?
No. Becky? Okay, there's bad charge separation here. Here you don't, on the right you don't separate charge. That may have been part of what Lucas was trying to say. But there's another way you can say it, just in terms of homo-lumo mixing. The language you're using is the language of resonance, right? That you don't want to separate charge. I want to see why, in terms of molecular orbital energies or atomic orbital energies, you get more stabilization here. Alex? Right, but that's true in both cases. There's an electron pair here that mixes with the vacant orbital. There's an electron pair here that mixes with the vacant orbital. Why is it more effective here than it is here? Claire?
Just guessing, but with the resonance, with the two structures on the left, when the resonance comes down to the OH bond, it's antibonding. But with the other one, because the H isn't there, it's actually making it more stable.
I have to think about that a while. But I want you to try again in terms of what makes homo-lumo mixings good? What makes them important?
If there's a high
overlap.
Overlap.
That's the same in both cases. It's the same oxygen mixing with the same double bond. And what else?
If there's a high homo.
If it's a high homo. How would you say, how would the homo here is an unshared pair on oxygen.
Right.
The homo here is an unshared pair on oxygen. Are they the same?
No, because the homo on the left is taken up by the hydrogen.
Right, okay. So the one on the left has another proton, which this one doesn't. that means that the electrons here are more stable, lower in energy. And this is a higher HOMO, which is associated, another way of saying the same thing, with the fact that that's a negative charge. When you have a negative charge, it's a bad place to put electrons. They're high in energy. Another way of saying it, and the way you said it, which is probably a better way of saying it, is that the proton is gone. So it's not stable. So you expect more HOMO-LUMO mixing here because of better energy match than on the left. Therefore, the observation that it's 10 to the 11th time stronger as an acid. So it's a higher HOMO because of that negative charge or the absence of a proton. Okay, so there's our carboxylic acid. And finally, the last functional group we wanted to talk about today, which is a really complicated one. I mean, it starts very simple, but you'll see it gets pretty baroque pretty soon here. So it's methyl lithium. And the chance of your figuring all this stuff out ahead of time is about 0, right? So don't be depressed if this looks like it's getting very complicated. Remember, there are 3 approaches here. One is to draw lines a la Lewis to understand how things come together. Another one is to use a computer to generate molecular orbitals, to break the total electron distribution into orbitals and look at them one at a time. And having seen what the computer produces, some of those orbitals are interpretable, as we've seen that they're anti-bonding in a certain region, bonding in a certain region, and so on. But the chances if you're competing with the computer in drawing accurate molecular orbitals, to the extent that molecular orbitals are real, the chance if you're competing with the computer is not very good. So don't expect that you can exactly draw them. But if you see the one that the computer has drawn, at least in some cases, you can make some guesses about it. You can see how many nodes it has, whether there are nuclei in the middle of lobes, which would make that unstable orbital, where it's bonding, where it's anti-bonding. Those kinds of things you can analyze, even though you can't produce them yourself, so don't think that you're going to be able to, right? But then there's another point of view, which is to look at localized pairs, bonds and anti-bonds, and how they'll come together, right? And that you can do. That's the intermediate between using just Lewis and doing the full molecular orbital kind of thing. This is something you can do in your head, and that's what we're going to show these different points of view of this one. So here's methyl lithium. Now, what will make methyl lithium reactive? What's a high HOMO of methyl lithium? Marty? What makes HOMOs, what makes for a high HOMO? What kind of things do you think about?
Not very stable, as we said. Maybe with the O minus.
Can't hear very well.
Like with the O minus in the slide before, actually pairs.
Just with a pair of atoms. I'm not trying to make like the slide before where you're doing all complicated stuff. But just you have 2 atoms, they come together. Will they give a very high HOMO? What determines how far they go up and down? The HOMO and the LUMO. What's one thing that determines it?
The overlap.
Overlap. Okay. So here are 2 atoms that are coming right together to a single bond distance. So good overlap. Let's suppose it's the same as all overlaps, okay? What else? What is it besides overlap that determines how far? The energy match, right? Now, what's special about methyl lithium? Methyl's not going to be funny. That's our standard thing. But lithium is funny. Where is it on the periodic table? Maybe that's the problem we're having.
It's
on the far left, which means it doesn't have a very big nuclear charge. So does that mean electrons are going to like being there or not like being there?
they're going to not like.
Because it's not much nuclear charge. So it's going to be a bad energy match, high energy. So there's going to be a high HOMO, right? The HOMO here from the carbon doesn't go down very much because of the bad energy match. Okay? So there's an unusually high HOMO. What will it look like? Where will it be? On the carbon or on the lithium?
The HOMO?
The HOMO.
But it'll be on the lithium.
Is it going to be symmetrical, or is it going to be more carbon, or going to be more lithium?
What? More carbon, because...
More on the carbon, that's the lower one, okay? So if we want to look at the HOMO of this thing, it's going to be mostly on carbon, not so much on lithium, and an unusually high HOMO because of the lithium. And there it is, that's the HOMO. Marty, you're going to finish us here by saying, what orbital does it look like?
It looks like...
I'll back up. There it is, and there's the orbital.
2p-ish.
It's a 2p orbital on carbon mostly, right? With just a little bit of lithium, 1s or 2s, pardon me, on it, but just a teeny bit of lithium, and it's anti-bonding between the lithium and the carbon. It's the, or no, wait. It must be a p orbital on lithium because it's the favorable one, it's the bonding one, right? We see the red, but there's a little, we see the blue of the lithium, but there's a little red on the other side that we don't see without making a net, which I didn't do. Okay, so that's the HOMO, it's a sigma. Now, what will the LUMO be? Kate, what do you say? What do you think for a LUMO of methyl lithium?
It's going to be lithium orbital because
Can't hear very well.
lithium or like
Yeah, the lithium has a lot of vacant orbitals on the atom, right? It comes in with only one valence electron. Only one of its 4 valence orbitals is occupied. So it's got, in fact, 3 vacant orbitals. So that's going to be the LUMO. There's the LUMO, mostly on the lithium. Okay? Now, but the LUMO plus 1 is this orbital, which I've drawn in a funny way at a relatively high electron density contour, making the things very small. Because if I made it bigger, it goes way off the top of the sheet and off the bottom of the sheet, because this orbital isn't held very tightly by lithium. It sticks way out. And it turns out to be out of the range that gets plotted by Spartan, so you get funny looking holes in the orbital. So I chose this particular density. But anyhow, you see, it's a p orbital, right? That's different sides, top and bottom. Now, so you have a, is this an unusually low LUMO? Monique, what do you say? Let me say something. I say lithium has a small nuclear charge, not a very good place for electrons to be, right? Which means that it's going to be very high orbital energy. Can you see any contrary things that say it might be unusually low?
I would think it would be high.
Can't hear very well.
I would think it would be high.
Because of the low nuclear charge.
Yeah.
Compared to what? What are we comparing with to say whether orbitals are high or low?
To carbon or
To carbon-carbon or carbon-hydrogen, sigma and sigma star bonds, right? So clearly enough, the carbon and hydrogen start lower in energy than the lithium does, but what? But they have big overlap. So sigma star is quite high, much higher than lithium, because it's an atomic orbital. It hasn't mixed with anything, this one. Okay, so it is, so methyl lithium has an unusually low vacant orbital and an unusually high occupied orbital, and what do you expect? You ever seen a case like this before where the same molecule was BH3? It's for exactly the same reason, right? Except more so, because lithium is more so than boron, being further to the left in the periodic table. So we can put 2 of these things above, up and down from one another like this, and have the HOMO of one be stabilized by the LUMO of the other. Kevin?
Sorry, could you please explain again why it has low LUMO?
Yeah, because it's an atomic orbital. It's not a molecular orbital. It's not a bonding orbital. It didn't mix with any things. The things we're comparing with are not carbon and hydrogen, which are in fact lower than lithium. It's the sigma and sigma star bonds of carbon and hydrogen, which, and the LUMO here is higher than that of lithium. Lithium's unusually low because it's still an atomic orbital, didn't mix with anything. Okay, so there's stabilization of the sigma by the pi, but at the same time, we can go the other way, and the HOMO on the top can be stabilized by the LUMO on the bottom, same as in BH3, giving B2H6. Okay, so these things dimerize. They come together, HOMO of one stabilizing the LUMO of the other, and vice versa. They move together, and you get a thing that looks like that, very much like B2H6, right? So you have two vacant lithium orbitals stabilizing the unshared pair of carbon. You can think of it that way. And it also goes the other way. The unshared pair on that carbon is stabilized by two vacant lithiums. Okay? So these are 3-center, 2-electron bonds, just as in B2H6. Okay, now, but remember, lithium has two other vacant orbitals, each atom. We've only used one here, right? So they can combine to give this. This is actually the LUMO of that dimer, right? Those are in the plane of the 4-membered ring, right? And there are other vacant orbitals too, like this pi one, which is in and out from that 4-membered ring, made up of p orbitals on the lithium. That's the LUMO +1 of that dimer. Okay, now I'm going to rotate this. Now, pay attention here, because the next picture is a little confusing. I'm going to rotate this thing so that we're looking just a little bit, we're looking mostly in the plane of the molecule, but twist it a little bit so we can still see the top of the molecule. And we're going to twist it such that the red lobe in back is behind the red lobe in front. So what we're going to do is rotate around that axis and shift it a little bit toward the center of the picture. So it's that same orbital, and there it is now. But it's a little confusing in the middle because there's one red lobe in the back and one in the front. Okay? We could draw it down. Okay, so that's what it is, but we're going to drop an axis that goes right through the middle of that parallelogram. Okay? And now along that axis, we're going to bring up another molecule, but it's going to be rotated 90 degrees. So those are the same two orbitals, LUMO +1, in both cases. The one on the bottom is rotated 90 degrees around the axis I drew. Okay? Now, will those things interact favorably with one another? And even if first they're orthogonal, and second, even if they mixed, you wouldn't care. Why? Because they're vacant. So what we want to do is look at the bottom, not at LUMO +1. We want to look at the HOMO of that one, that dimer, which looks like this. And now you see something neat, that the blue in front overlaps the blue vacant one, and the red in back overlaps the behind red vacant one. So the electrons in the HOMO on the bottom get stabilized by overlapping with the LUMO +1 on the top. And of course, by the same token, the HOMO of the one on top overlaps with the LUMO of the one on the bottom, like that. So we already had two molecules come together to form dimers. Now we're having two dimers come together to form a tetramer. Yunju?
Why are we using LUMO +1 instead of?
Because that's the one that does the overlap. The actual LUMO doesn't overlap this one on the bottom. Okay. Lucas?
Does that make the LUMO +1 essentially the new LUMO because it's more stabilized?
Well, but it mixes with this one. So the LUMO +1 and this one interact. Right, here's the HOMO.
And they make it
LUMO
better than
+1. So okay. So
Okay.
So it contributes to this one. Right? When the HOMO here of the dimer mixed with the LUMO +1 of the other dimer, you got a mixture. This one looks mostly like the HOMO of this dimer, but it's a little bit helped out by looking like the LUMO of this one. There's a new vacant orbital, but it's still higher. You don't care about that one anymore. Okay, so now we can take two of these and bring them together. That's a bonding, the orbitals we just showed. And you get a cube, right? So here's the one on the bottom, 1, 2, 3, 4, and here's the one on the top, 1, 2, 3, 4, and they've been turned 90 degrees to line up these orbitals, and they come together, and the electrons to get more stable. Now that used on every lithium another one of its vacant orbitals, right? But what, Angela?
There's another one.
There's another one. Okay, so the HOMO now turns out to be this, and you can understand that, the biggest part of it, by seeing that it's a 4-center 2-electron bond. Mostly it's a p orbital or a hybrid orbital of the carbon, an unshared pair of carbon, but it's stabilized by 3 vacant orbitals of lithium. So 3 vacant lithium atomic orbitals stabilize the unshared pair of carbon. But, as Angela points out here, there's another one. That's still a vacant orbital on lithium. That's on the top lithium. There are other ones on the other 3 lithiums. So we need more electrons, or it's capable of stabilizing more electrons. Where do you get them? Well, you might think you bring another cube up, but in fact there's something easier to do because this is done in solution. And the solvent is dimethyl ether, as shown here, or some other ether, which has an unshared pair of electrons, and it comes along and gets stabilized by that. But at the same time, the other 3 oxygens, the other orange balls, the other 3 lithiums, I should say, stabilize oxygens of other ethers. So you have 4 ether molecules associated with the tetramer of methyl lithium, and this is about as complex as we're ever going to get. Right? So I think you would have had a hard time at the outset predicting this. But having seen it, I think you can understand it. That's what we're aiming for at this stage. Because as we go on and get lore that this reacts with this and gives this, what I want you to be able to do is to look at it and say, aha, that's what happened. That's why that reacted that way. Not necessarily. In some cases, you'll be able to predict. But in other cases, you'll be able to understand and correlate it with what you know. So if you put more ether in, if you have a lot of excess ether, then it rips these things apart so it can fly apart, and you get a bunch of ethers on every lithium, right? And in fact, this is a further development of organic chemistry beyond what we usually do in an elementary course, which is to understand the non-bonded interactions, because often you wouldn't consider that oxygen-lithium to be a real bond. It's just sort of a weak solvation thing, although truly it is a bond. Okay, so these so-called non-bonded interactions and the effects of solvent are a vital part of lore, what solvent you choose for a given reaction. For example, if you want to facilitate ionization, you use certain solvents and not other solvents. And we'll talk about that a little bit, but I just want you to show you what there is out there beyond the bonding that we've already talked about. But we've really taken theory pretty far here in the first half of the first semester of the course. Now, I said we would vote, and I forgot to bring a piece of paper. I have this piece of paper, but I'm not going to use it for that because this is the thank you note. So if you haven't signed it, let's pass it around because there are a few people who haven't signed it. Let's pass it down, back and forth down the aisles. I think most people have signed it, but some haven't. You don't have to. And you also don't have to contribute, but if you want to have a sense of satisfaction of having contributed to the class gift, you can leave a small coin on the table over there. Okay, but the other business we have to transact is, I'm going to give a review session before the exam, but it's not obvious when we should give it. So I've decided that the easiest thing to do is to see how many people of course we want people not only that can, but would come. Right? If you could come but wouldn't, you're irrelevant. So the question is, how many people cannot or would come other times but cannot come at the time shown? And the one that has the fewest will win. That make sense? Okay. So how many people cannot come Thursday evening, 8 o'clock? That's too many. How many at 8:30? Here we have about, my judge is about 15. How many cannot come Friday afternoon? Whoa.
Loud.
Okay. How many people cannot come Saturday early? That's a lot. That's about 20, I say. How many Saturday at 10? How many Saturday at 2? How many Sunday 1 to 3? Well, bear in mind that there's also the TA session Sunday evening. I think it's better if I do it, 2 days before the exam rather than the day before. But on the other hand, none of these earlier times can get, there are always at least 15 people. Let me see about the option 2. That was the one, Thursday at 8:30. How about if it were 9? How many could not come if it was at 9? Thursday evening, tomorrow evening. That actually is a little, and let's see Sunday again. Sunday sometime early afternoon. There are actually more who can't come on Sunday than Thursday. So I'm sorry, but it'll be Thursday. It could be 8:30 or 9. Does it make a difference? Is there somebody who'd come if we started at 9? Pardon me? Saturday what? Saturday was pretty bad. Well, let me see. Saturday 9. Yeah, that's worse. Saturday 10. Saturday 2. Saturday 8 p.m.
8 p.m.
Okay. So it'll be tomorrow. It'll be tomorrow night. It'll be tomorrow night at 8:30, and I'll send you an email once I got a room. Okay, let's continue. Okay, so to summarize the first half of the semester, we've seen amazing modern tools that show us molecules, the real thing, at the level of angstroms and at the time scale of picoseconds, 10 to the minus 12 seconds. We've seen scanning probe microscopy that can feel atoms and X-ray diffraction that can see them and can see bonds with difference density. We've seen spectroscopy, IR and ESR, and next semester we'll talk about nuclear magnetic resonance. So they're amazing tools, not only experimental tools, but theoretical tools, this stuff about quantum mechanics, and people believe quantum mechanics enough that they talk about doing calculations on a computer as experiments, right, rather than just things you do in the lab. So that's amazing, right? And it all has developed fairly recently, say since the time, most of the important things we've talked about have developed since I was in graduate school. But what's amazing is that organic chemists were not at all surprised when they were finally able to see these things, because they already knew what they looked like. So it wasn't surprising. It was satisfying, and there were a few little queer things that are understood better now than they were before, certainly, right? And things like being able to generalize about what makes a functional group, that's completely new, right? But fundamentally, what molecules look like and how atoms behave and that this reacts with this, that was already known. So how could they possibly know it when they didn't have these tools? And that's going to be our chore for the next quarter of the semester, is to figure out how they knew. How did organic chemistry really develop? And a reason for this is that if you know how it developed, then you understand the language much better, because the language we use isn't the language of quantum mechanics usually. It's the language that developed during this long gestation period. And it started, as we said before, in the 17th century, and we've gone on this, and we've talked now about science, the scientific method and force laws, and how we finally found out what the force law was for atoms, right? And in the 20th century, this whole theoretical experimental stuff came together, and we saw that bonds were shared electrons, and we could see them, and the quantum mechanics could help us to understand them. But we've left out this middle period, starting with the end of the 18th century with Lavoisier discovering oxidation, and ending with the discovery of quantum mechanics, because this is the period during which most of organic chemistry developed, and we have to see how it happened. Okay? So this, if you've been here 107 years ago and been graduating, you would have been in this picture with your fancy boots and so on, right? This is the computer science building. You walk up. Now it used to be the chemistry lab. On the right, you know where it is? Watson Lab down there. Okay, so let's look at see what they understood at the time. They chalked things on the bricks to show off their knowledge. So here's CH4, methane, obviously they knew that. And here's the reaction of sulfuric acid with zinc, which gives hydrogen. They knew that. And here, what do you think that crazy thing is in the middle? That's a benzene ring. And remember how it looks like what they confirmed at about the same time the clairvoyant people saw that the valences all went to the center? Okay? And down here you see another thing. Those are probably aromatic rings with the double bonds not shown. But an interesting thing that's shown is that the Greek letters alpha and beta there. Those are symbols that are still used to denote different positions that you can put substituents in the ring. Okay, this is inside the chemistry lab, which was in where SSS is now. And you see things like this, right, which came from that lab, I'm sure. There was a big box of them floating around here, and I rescued one of them a long time ago. The others got thrown out, right there. And what's that second arrow? There's another important tool. A Bunsen burner, right? Bunsen invented the burner about 1860 or something like that, or 70. Okay, there's one that looks just like this, right? Actually, this isn't that old because it says on it West Germany. So it's interesting. Okay, there, what do we see here, the white thing? Mortar and pestle, they could grind things up, right? And there, what's that? It's a burette drying upside down. Notice, that's the only quantitative tool. Right? So, were there any other quantitative tools in this picture that they were showing off?
Well, there's some burettes on the side.
Aha, they're burettes. Anything else that will give you a number? But that's just a crude balance, right? They had analytical balances, but they weren't portable. They couldn't schlep them out to Prospect Street for the picture. Okay, but that was it. Okay, this guy here looked like that. C. Malin Klein, class of 1901S, and you know his name because GlaxoSmithKline, and he gave the money for the Klein Biology Tower and the Klein Chemistry Lab and the Klein Geology Lab too. Right? But you could also measure angles on crystals, right? But that's about it. Somehow with these tools, they figured out where atoms were in molecules. Isn't that crazy? So if you look at the front of the building, you see down here, he's wrapped in stuff now because they're painting him. Benjamin Silliman, Yale's first scientist, or first chemist anyhow. And he's holding something. Can you see what he's holding?
Crystal.
A big whopping crystal, right? That's where science was at. That's what he's mostly known for, is mineralogical things. Okay? But here on these plaques is something else. This is the names of the people who actually developed all this stuff during the 19th century. So it starts in the 17th century, actually, with Boyle and the gas laws, but that was way before. Notice he was born 120 years before the time we're talking about, Lavoisier. So things happened, but not a lot from our purposes during that period, and it really got underway with the second person. These are in chronological order. The second one is Lavoisier, and that's where we're going to start. And then Gay-Lussac, Alias, Faraday. We're going to talk about these people, okay? And here is you and your cousins who did all this stuff, because we have a family tree here. So there's you and me. And I studied quantum mechanics as a graduate student with E.B. Wilson, right? Who was a postdoc with Linus Pauling at Caltech, who did X-ray and proteins. He's the first guy that saw the helices of the proteins, okay? And another postdoc of Pauling was Jack Dunitz, whom we've talked about a lot. So Dunitz, who we've talked about a lot, is your great uncle, academically. Okay? But if we go back early, and here are things, notice how many of these things, the 20th century things we've talked about. The shared, notice that boldface is things that are experimental, and normal face is theoretical things. Shared pair bonds, mesomerism, which is resonance, electron pair shifts, the curved arrows, quantum theory, reaction mechanisms. We already talked about ammonia being oxidized by chlorine, for example. IR spectroscopy we talked about. We haven't talked about, well, we talked a little about polymers, not much. We haven't done mass spectroscopy. Well, we did actually in the problem set in the first thing, right? Conformational analysis we'll do at the end of the semester. X-ray, we talked about NMR next semester. Molecular orbital methods we've talked about a lot. This is what we've been talking about. That we'll do at the end of the semester. Non-covalent structures we just talked about a little bit. Scanning probe microscopy is quite recent, so on. So we've actually talked about a lot of this stuff already, the more recent stuff. But what we want to talk about now is the earlier stuff, how people discovered things in the 19th century. So these are the guys that did it. And in particular, we're starting with Lavoisier. But Lavoisier was not the first altogether. But I'm going to have to wait till next time to tell you who was first.